Okay, this is what I would certainly call a difficult lecture coming up here, but it's fall break next week, so rest up after this thing. The algebra of the Lagrangian for the Trebuchet equations is the main topic today, but in the process of describing that, I want to return and review covariant, contravariant geometry. This is stuff that's on homework for next week, and we need to use it quite a bit for the rest of these two chapters and beyond. The basic idea of the covariant, contravariant, what physically they mean, but also mathematically, how they relate to Jacobian, or its inverse, the Cajobian. The coordinate transformations also, a bit of geometry and algebra there. But when we start to make use of this for the equations that we've derived already, the Lagrange equations for the trebuchet, remember what happened in polar coordinates. We had to, after we got done just writing the Lagrange equations down, then you actually have to take the time derivatives in order to make an equation that, well, if you're going to put it on a computer, that's usually the best way to do it. So let's go ahead here with the, there's not much to add here, although we're trying to get the analyte thing to be working on these modern systems here. Now, in order to run this particular computer, I need to stick the Bluetooth object in there. And now, this is the beginning of the thing here, just a review of what we have done so far in terms of the development of Lagrange equations in general. And if it's the Lagrange force equation, which is what we're going to be doing most of today, then the force vectors or force components are explicit, and you just have equations for P dot for both the angles of the launch arm and the projectile arm. That is the little, well, it's a string in our particular little model here, or a rope. And if we have gravity as our only force, and it's a conservative force, as indeed this particular system that we're talking about has, equations become very symmetrical. So at this point it doesn't look like we have much to do as far as the algebra, but that's not the case at all. We have a lot to do, and that's going to take up pretty much all of the class today, particularly since we have to review the geometry of covariant and contravariant. Okay, so let's recall again the sort of coordinate systems that we're dealing with here. They are 2 to 1 value, that is multi-valued, bi-valued, and that means that we have a funny kind of torus on which all of the motion takes place. The angles of theta and phi are quite evident here. I showed you last time that if this guy stays constant, then the other angle, the projectile angle, makes a circle. And the same thing is true if I hold the projectile angle and just move the arm of the trebuchet. The projectile angle is laboratory relative, that is, that angle does not change as this thing rotates, but the result then is that you have it's just like thinking like a compass and drawing this arc right here, and then the arc for this one occurs when the trajectory, when the trebuchet goes over either by passing this point or passing that point to from a left-handed trebuchet to a right-handed trebuchet. So that I want you to keep in mind for this discussion of covariant. These are the covariant vectors theta and phi that we're going to be deriving algebraically. But remember also that we'll be doing differential geometry. That is, we make a little microscopic box here which shows what the trajectory, what the coordinate system looks like. And this is a coordinate system that has the name, and I didn't write it there. I'll put it up on the board here very quickly. These, if you are dealing with mathematical literature, you speak of affine coordinates. These are coordinates that are GCC. This is the technical name for mathematicians, but our generalized curvilinear coordinate systems. And this, when you put A in front of something like asymmetric or just about anything, I think atheist, okay, it means not or without. So this is not fine, I guess. That's the only etymology I can give you. Is that the coordinate system is not orthogonal. It's basically one that has little parallelograms making it up if you look at it with a microscope. So what we're going to be discussing is that geometry, and that's one of the problems that I've given you this week, is to look at a diagram that has blanks in it and fill it with the correct geometrical notation. So let's take a look at this thing up close a little bit there. The basic idea of the coordinate system is it is on a three-dimensional drawing there. That's a trick that we try to do whenever we can, make some subspace show up in a way that we can visualize it. The actual coordinates as they're drawn, like that one right there, or let's go ahead on this one, that particular drawing there, showing the marks being made, green and blue coordinates. For green is the projectile angle phi, and the blue is the theta of the launching arm, the big arm. Those trajectories look like a three-dimensional object. And that's true of a number of graphs, including the ones that I've given you sheets with the graphs of the two that I want you to solve. The basic parabolas that are either on top of each other, I call that the plopped parabolic system, and then another one where the parabolas kind of slide. They look three-dimensional, but like this one, they're not. On the actual paper here of x and y coordinates, they're flat. They are in that plane. So we will, it's just something to be careful of. Okay, let's see if there's anything else I need to point out here that we did in the last lecture. I think that's enough. Now the same thing is true here back in lecture 9 when I was just showing polar coordinates. And I actually tried to draw a picture of an arbitrary sort of GCC, an affine coordinate system, and that involved curves that, as I say in this note here, it's a 2D drawing, and there's absolutely no 3D perspective at this level that we're talking about these curves. So that is what we talked about back in the review unit 1, and the Cajovian being the inverse of the Jacobian, and this is the Cajovian. So the rows of the Cajovian give you the contravariant vectors. Then the columns of the Jacobian, that's where you have the Cartesian coordinates in the numerator, and the whatever the curvilinear GCC queer coordinates, Q's, in the denominator of the derivatives. here they're flipped. And that gives you in each column the covariant vectors. So that's a good procedure to remember. The first thing you got to do for mechanics of this sort, this algebraic mechanics, is get the Jacobians. Inverse of that is the Cajobian. Both of those vectors you need for various things that help us solve these problems. And the other thing was back in lecture 9, and let's get this up here on all the screens. The other thing was the basic idea that the first differential in terms of curvilinear coordinates involves the Cartesian in the numerator, the GCC in the denominator of the derivative, and that means then that this is a chain rule for the differential R, and therefore these vectors, which are sitting there and there, E1, E2 sub covariant, are tangent. So that's the tangent space, and then the opposite of that is obtained from the Cajobian, which has the the contravariant vectors here involving gradients. That is, the thing that we're looking at here is a combination of the gradients for the coordinates 1 and 2. And so they're just sticking out wherever they stick out by being perpendicular to their respective q equal a constant. Here's q2 equal to a constant. It will have a vector pointing normal to that. This one, q1 equal a constant, has an e super 1, a contra vector pointing normal. Okay, so all of this is going to happen again for us in the curvilinear coordinates of this trebuchet. And the basic idea, of course, is that co and con make a nice Kronecker delta. That is, they are 0 unless m is equal to n, and when they are equal, you get exactly 1. So these vector here is in a sense the inverse or reciprocal of this vector and vice versa. Let's see if there's anything else I need to say about that. That will play a lot of role in the physics that we use as we take advantage of this GCC system. So let's get all that stuff up here. Now we're going to do, as I say, both the covariant vectors coming from the Jacobian, and then we'll do the contravariant vectors coming from the inverse of the Jacobian, or Cajobian, and also develop both the covariant and the contravariant metric. That's we have to do that in the next few slides here. So let's go back to just look again at page 20 of lecture 14. So lecture just preceding this one, and we need to do a couple of derivatives here in order to complete this calculation. So have the coordinates of the mass, and we're building just from the geometry of the coordinates, in this case of the projectile. Now the arm has its coordinates 2, and if this were a 3-arm trebuchet, this is something we thought about trying to build. It's a way more complicated system, but one that would, if you calculate what you get just like when you take the super balls with 2 balls, you get this nice throw of a little thing based on momentum conservation of a big thing. And then we have with 2 levers, you see an amplification process in an angle, okay? A lot more complicated than the physics of the one-dimensional track that the super balls fall. But the basic idea is with 3, this thing would really be deadly. I mean, it's approaching what you would make if you had a whole bunch of particles, then you make a bullwhip. Okay, you get tremendous amplification if everything works right. And anybody want to participate in a project to actually make that thing? That's what sort of in my dreams, okay? Weird dreams, but that's, you know, it also is that these things have relevancy for molecules. I mean, some molecules have what's called floppy molecules, that is, atoms or sets of atoms that essentially are loose, rotating around something, and you would get some interesting physics in the quantum regime for increasing. I mean, this is all pipe dream stuff, but I'm pointing that out. Now, what started me off on that was that right now we're just writing the equation of the most difficult part of this thing, which is the projectile that's riding on this arm. We've already got the polar coordinates for this one, so we don't need to do that. But what we're doing here now is just building the G mu nu metrics that go with the coordinates of each of these things, and then we can put that together. And then that metric turns into the gamma mu nu when you put the masses on all of the things and assemble it. So I'll be making this point again, but I want you to be aware of that difference here. So first step is to take the derivatives that we need to make a Jacobian just out of the x and y coordinates of the projectile in terms of the two angles, the only degrees of freedom that this particular mechanics problem has. So there you are with the two covariant vectors coming out of the columns of that. It's really not that different from a polar coordinates, it's just that it's doing it with angle phi and theta together there. And let's keep us lined up here because this algebra gets fairly complicated, and this is what we're building right now, is the actual vectors theta, e sub theta, e sub phi, which are the covariant ones, the ones that go along the actual tangent lines of this toroidal coordinate system, crazy toroidal coordinate system. Okay, now there's the other side, of course. The inverse, a 2x2 inverse, just to remind you once again, you stick the determinant here, you switch the diagonals, and you put a minus sign on C and B. That's something you don't get to express quite so simply for 3, 4, 5, and so on dimensional matrices. In any case, very quickly we get this determinant, and this Jacobian, or in this case we're talking about Jacobian, but Jacobian matrix, when it is singular, and that's when this goes to 0, something's wrong. You're in an area where the coordinates aren't working very well. Well, where would that be? When these things are, when the trebuchet is stretched out, if I take this mass, swing it around here and get it so that it's lined up with its throwing arm, you're right on the outer equator of the torus. And when it comes around that circle down and goes under or onto the actual throwing arm, once again, with this time theta minus phi being either pi or 0, well, that's when this is going to go to 0. And so the difference between those two angles, the product of the radii, is what you see there. And it's telling you that the coordinates have collapsed. The cells that make up the affine coordinate system have collapsed. And that's what I'm trying to show in those pictures there. Let me go back on this one quickly here. But actually, I don't want to go back. I'll just go ahead and move forward on both of these. So this is what we're looking at in terms of covariance and contravariance for the calculations that we need in order to use generalized curvilinear coordinates effectively. Okay? Now, the singularity occurs here
whether the determinant is 0 or infinite. These are reciprocals of each other. So if that thing goes 0, this one goes to infinity, and your coordinate system isn't working, you're on what's called a caustic of the coordinate system. Or if these were waves making the coordinates, a caustic is an optical term that reflects some interesting behaviors, like the ripples on the bottom of the swimming pool and all that sort of stuff. Okay? Now, contravariant vectors here as opposed to covariant vectors. Well, in terms of those coordinates, they just point out and don't look like they're very useful. It looks like this thing that's got the tangent space labeled is more useful, but the normal space is valid as well. So that's something we need to make sure we can see. So I'll get all of these up here. Now, before I go there, let me just point out once again that these things are orthogonal. That is, mutually orthogonal. Dot product of any of the covariant with the contravariant gives you absolutely 0, no matter how these are scaled. But these are particularly scaled. This one, the last thing, the contravariant, so that when they dot products occur, you should get 1. So there are all kinds of checks as you go through a calculation like this to see if you're on the right track and not making a mistake that you have to correct and then redo everything. So this is just what we did back in lecture 9 in the review with polar coordinates. And what we're after are the not the actual metric coefficients, the metric tensor, in this case labeled G R phi or G whatever, G 1, 2, and so forth, for the what we would normally be using just to track the geometry of either covariant or contravariant. Okay, let's see if there's anything here I need to point out. Yes, after you get done doing that, that's what we would like to have. So the it comes down fairly simple. This is the thing that's sitting as a denominator up there. Now this in particular case gives you the cosine of the difference of the angles off things. So when the difference of angle phi and theta, wherever that is, and it doesn't matter where the beam, the big beam is, if the other beam is 90 degrees to it, it looks like at that particular point you have an orthogonal coordinate system, but everywhere else you don't. So this is only 0 for a 90-degree difference. And then this one is a 0 at 0 and pi, stretched out or completely overlapping. All right, I think that is all we need on that. We have them all listed on this particular slide here. After I go through there to there. Okay, so here's the whole story right here. Both the covariant metric, called a metric tensor, but it's just a matrix like all of the other things when you're represented. So here, the difference, main difference is, first of all, you'll notice that it comes out with the L squared and the R squared switched from R squared, L squared. It also comes out with a minus sign on the off-diagonal component. This is equal to that. These geometric coefficients are making a symmetric matrix. This is always equal to that. Obviously, dot products commute. So whatever this one has, this is the inverse of that matrix, just like the Jacobian is inverse of the Kajobian. These metric coefficient matrices share that property. So that's nice. That's important too. I'll have that for lots of things, especially when you're doing relativity. Metric coefficients and general relativity are very key to the beginning of the theory. So, other thing I should point out is that if you take the transpose of the Jacobian, multiply it by the Jacobian, you will get the covariant metric tensor, which is the one that's most used in gravity theory. But we're going to be using the contravariant one when we discuss the Hamiltonian approach to this particular problem. Hamiltonian, remember, uses the contravariant metrics and momentum as the main variable, the main independent variable. Okay, I think that is about it, except for pointing out, which I'll do very quickly at the lower left-hand corner of these screens, that the product of the Kajobian with the transpose of the Kajobian would give you the contravariant metric. So all of these, normal space, tangent space versus normal space, all of them play pretty much the same game with each other. Okay, and that's where we need to really take a look at what these coefficients are doing for us if we consider, now here I'm showing the microscopic view of that torus coordinate system. I don't have a three-dimensional view of the contravariant situation because of the normal vectors. But I can always imagine that I have a coordinate system that's based on the contravariant vectors. That is, this is what is called the normal space for mechanics and the kind of relativity that uses this geometry. It's very often not mentioned, and in fact it's really difficult to do drawings when you're dealing with four independent variables, x, y, z, and time. But here is what I want to first point out is that there's a number of ways of using of representing the components of a vector in this affine, not fine space. And that is, you have two choices. You can either drop along the line, make a parallelogram here, and say that this vector here is a combination with some components that we're about to calculate here of a vector that's proportional to E sub phi, the covariant phi, and then E sub theta, the covariant theta, has another one. I guess the parallelogram side is important in order to do that. Well, the basic definition of a vector in terms of the covariant vectors, which have contravariant components, the idea being that this thing transforms inversely to this, so that when I do imagine a transformation, it is not having any effect on this vector. The vector is just, if I have a new set of covariant and contravariant vectors that I'm indicating here with little lines over them, E bar we'll call them, and then there's a component that goes with it, V bar, particularly if you were doing. So this would be, say, one vector, and this would be another vector. But the idea of all of this is that these vectors represent some piece of machinery or some device, and these are just different ways to look at that. I can look at it using the unbarred vectors and coordinates that are drawn here, but I might have some other completely different system, like in your homework, I've given you the plot for a parabolic system, and you have to, for some reason, do a transformation to the sliding one, or back to Cartesian, whatever. So the idea of being able to have complete freedom in the mathematics of going from Cartesian to these coordinates and then to some other completely weird coordinates, the barred coordinates, say, is important. Really a very, great piece of mathematics that Riemann and other people have given us here. So, that's just one way to look at it, the way you're used to looking at a vector sum. That is, I have a vector sitting here, and it is literally a sum of this vector and that vector. It's the sum of these two terms, and the question is, how do I get away with doing that, because these vectors are not unit vectors. Okay, so I have to look and see what it is, the absolute magnitude of, say, the term e theta, e sub theta, v super theta. What is that? Okay, so, well, this number is just a scale factor, but the actual length of this vector, that's the square root of e theta dot e theta, that's the square root of the metric coefficient d theta theta. Okay, so that's an important thing to realize. And therefore, you see, the actual length of this vector here is the component that we'll be using for the phi, and multiplied by the length of the vector that is the contravariant vector e phi. Then theta plays the same game. It's got that extra scale factor. This is all drawn out right here for this one, g phi theta theta. So that's how you do it if you're working in a tangent space and thinking about this as a sum of some length along the vectors that are being used, covariant phi, covariant theta. Okay? I didn't follow quite here. Let's make this one show up a little bit more, and go ahead and move this one up as well. Because there's another way to do this. You can do a projection component. That is, you can just simply draw a line normal to the line that is the e phi line. This one normal to the e theta line, okay? Well, when you do that, you're saying, I'm interested in this thing here as a, I'm thinking absolute value of this thing as a v dot e unit theta. That is, this vector here dotted its projection on the a unit vector associated with that direction. And what is that unit vector? It's just the actual vector e theta, or e phi, we should be pointing right at this one right here, divided by its length, the same length that we used down here, but now it's a reciprocal of that. So that's what we're dealing with when we play with making linear combinations using the projection coefficients. So all of this is stuff we're now having to pay the piper for having GCC coordinates, which are not unit vectors, and they're not orthogonal. Of course, we've made that point before, but here's where the length of them comes in. Okay. Now, the other thing that's important here is a contravariant vector can be written in terms of covariant vectors. That always has to be the case. That is, these are all sitting on the same white board here. There are the contravariants that we were just working with. Now here's the normal space that goes with the contravariants. Okay, and there they are being orthogonal, like contras are, to the coordinate lines of this particular coordinate system. But they're along whatever this space is. You see, now these are the oddballs. They're perpendicular to these vectors. So you see, GCC gets to be pretty complicated. And it takes a bit of bookkeeping to keep track of all of these things and be able to use them. And that's what this homework's about. Okay? So you get a chance to do some, just with 2 dimensions. There's one 3-dimensional one in there to see if you're really up for this stuff, but most of it's 2-dimensional. Okay? All right. Let's see if there's anything else I need to. So these coefficients right here are the ones that people go for at first, but they should go for the partial derivatives of the Jacobian first. That's more fundamental than the metric. Remember, the metric tensor is a product of JTJ if it's covariant that you're working with. All right. Let's see if there's anything here. Yeah. This is a little aside, but it's an important one, so let me make that fairly clear. What I'm trying to write here is that I can write any vector in terms of some number and then a covariant vector, sum over the ends. Now here's the dummy sum rule at work here. So I'm summing over n equal 1 and 2 to make 2 terms here, just like I make 2 terms when I express any of these vectors up here using what we've got pictured. And this coefficient right here is the contravariant vector m has a contravariant component n, and that is exactly GMN. So we need a couple of ways to show this. And there's a similar thing. Let's see if I have it here. This component right here is just the dot product of EM with EN. So therefore, and this is super contra. So it's the contravariant metric scalar product that's showing up there. We need to play with these relations a little bit more here. But basically, the idea is to be able to turn any number up here in terms of all of the other numbers that are there. That means involving u's, u bars, v's, v bars. And same thing with the vectors. Each one of these vectors should be expressible as linear combinations of all of the other things, you see. So you've got quite a lot of work sort of lined up here, but if you do it in an orderly fashion, relations like this become pretty obvious after a little bit of practice. Okay, let's go on and spell that out. There is one more thing here for the same for covariant vectors. To deal with a covariant vector in terms of a contravariant vector, you use the covariant metric. So the basic idea here is a sum over the m's brings me back to a particular covariant vector, the nth one. And this is a sum over m's on this side. So these are the 2 relationships that some people call this the index raising operation. I'm sorry, yes, index raising. It's got its 2 indices up in the air, and it's trying to pull the ends there, pulling it into a contravariant vector. And then the opposite of that is the inverse of that matrix, which takes the contravariant, turns it into a more civilized covariant vector. All right. I told you this was going to be hairy, but you know, it's one of those things that you kind of have to practice. It's one of these things where watching somebody else do push-ups doesn't necessarily make you very much stronger. So we're trying to make it as easy as possible. Make sure you don't waste a lot of time learning this. Okay, so we really want to compare tangent, normal, covariant, contravariant as transformations. And this is the weird way we do it. And let me get it on both screens here. And this one. Okay. I call this the chainsaw sum rule. I mean, we talked about chain rules, right? Well, this is the chainsaw sum rule. Okay. The basic idea is if you're interested in a particular contravariant vector, say E super M, I'll point to it over here so I don't cover anything up with a motion picture here. The E super M, that's defined as partial of Q super M. Got to match the upperness of the M's with respect to position vector. So you chainsaw this thing and slide the two apart. And then you do whatever you want to put here. And I want to go to the barred coordinate system, so I would put in the partial of the Q bar, M bar, twice. Just put it in there, and it's a sum over those. That's it. This is the contravariant vector of the barred coordinate system, summed, and the index down here is right where it should be, so that they cancel. That is, you have contravariant canceling contravariant left with covariant. And that's pretty much it. That sums up all of the transformations, actually including the metric thing we were just talking about. But that's fairly powerful. It's a slick notation that lets you pull this off. Here's another example here. I've got a partial with respect to Q sub M. Okay, that's the inverse of this. This is a covariant vector now. Chainsaw a summit to leave two blanks, which I then fill with whatever coordinates. And if I want Cartesian coordinates in there, I put those in there. That would just be my Jacobian or Kajobian that I started with in the beginning. But this lets you go to another GCC system that's completely different from the one you're working in, the barred system. Okay. Well, when you put this one together, you see right here, partial R with respect to Q bar, super M. That's nothing but the unitary barred vectors, sub M. Okay, the super M is down here in the denominator, so that makes it be in the lower part, the covariant position for that formula. Okay. So this, I think, is really key to this business. Now, what else is it you study that is like this? And this kind of goes without saying, and usually the quantum mechanics professors are very quick at telling you what it is that's going on. But once you have this, that implies, this is an easy thing to show, I'm going to sort of leave it for you to take it out of this relation right there, but this rule here of taking a contravariant thing, transforming it into a barred contravariant thing, in this case they're vectors, it works exactly the same way. It's the same set of, same super Jacobian. This is a super Jacobian. You have two GCCs in it. You use the same one to do the components. That's a big saving, because those components you work with most of the time. Vectors are just out there as placeholders. So that's really a key idea. And this one here implying the same thing now with the components. V sub M transforms just like the actual vector M into a barred component. Okay, so you got to give credit for credit is due, I think, in this mess. But this makes for a system that works very well, as long as these Jacobians aren't singular. And that's, of course, where you're always going to be having neighborhoods of singularity. Okay, now where is it that you've seen this? You remember writing in quantum mechanics as a vector, say a ket. A ket is 1 times m, and what is 1? It's a sum over ketras of the coordinate system that you want to go to, right? And then there's a coefficient right there. So that's just giving you a transformation coefficient that's analogous to this thing. Dirac notation equivalent. Okay? Same thing over here. And here are the components having the same transformation as the actual ket vectors do here. This is a good thing to make a connection between the crazy stuff you do in a complex Hilbert space, okay, of quantum mechanics, or even in a complex Banach space, that's a continuous Hilbert space, which is hell on wheels as far as mathematical properties go. But you can use this, and the sums become integrals, provided you use like measure and all that kind of stuff. Okay, but these things give you an insight into mathematical physics that, so they're not, it's kind of all the same stuff. It's called a dual space, Brockhead, or covariant, contravariant. Okay, they're analogous.
You
Okay,
can see it up there when they're side by side like that. You can envision a barred coordinate transformation over here that takes you to a coordinate similar to this side, and then vice versa. And in your
With
mind, if you
vectors.
do that at the same time, there's that one point right in the middle, and that's your dual.
Yeah, it helps you. It helps. It takes a while to build those memory paths, but when you do develop them, then things get a lot easier. Okay, let's see if there's anything else I need to put here. Oh, here's something where the thing kind of breaks down. I wanted to make sure you see the metric relations, where you have a simple linear transformation that takes you from covariant to contravariant, and then the inverse of it takes you from the other way. Okay, we don't have that for the brackets. They are different spaces, right? But there's interesting quantum mechanics where you make them the same space. Okay. That I will leave you for a discussion later, maybe. Ways to get weird in this business, they're quite numerous. Okay, the next thing here I want to point out is that most of what we've been doing here has to do with making relationships between vectors, which are just lines. But certainly in relativity but any sort of physics that you would be using this for, it's really important to realize that area is a key concept here. So how do we make a connection to area, say for the tangent covariant space? Well, when we showed the vector doing the little components here, it involved the square root of the metric multiplying the component theta, and then the phi metric, same thing, multiplying what we would call the component v super phi of the tangent space. Together they make an area. Okay, so what can that area be? What we're talking about here, and this is supposedly a linear quadratic form that we're making, we can take the components outside here and do call that area E1 cross E2. That is the square root of E1 cross E2 dotted with itself. And then I'll just use the epsilon tensors and all that. I'm skipping that. This is the A cross B relationship where I get the dot product of E1 and E2 of themselves, and then the cross dot products right there. Well, what the heck is that? Is that something we can recognize? And the answer is yes. It's this particular 1, 1, and 2, 2 geometric coefficients, and then the 2, 1, and 1, 2. Of course, they're equal, so this is squared. This one is just a product. Remember, they are the same dot product. And so what you've got there is the determinant, but it's the square root of the determinant of the metrics. Well, this wouldn't be surprising if you knew your Jacobians, because what we're looking at is a Jacobian here. Okay, so that's one way to think about this. And when you go to the contravariance, you're on business. Now I'm getting a little behind in keeping these things in sync. Let me go ahead and get that all up here. So this lets us take care of two vectors make an area. You've got three. We don't have that here because we don't have that many dimensions to play with. We better get volume by this same token here. I'll go ahead and start that down here at the right hand side. Well, let me put a couple of things in here just to point out what it is that we've got. That's the complete slide right there. covariant, contravariant products. We've already talked, I think, enough about that. But to go ahead, here's volume. Okay, and we're, I think, all familiar with the triple product of vectors. And what we're making here is the determinant, again, of metric coefficient matrix. Okay, but it's the product of Jacobian transpose and Jacobian. So you get your volume. If you like, just go back and work with the Jacobian. Be my break. Yes, that's, you don't have to worry about this. That's really all you want is the volume. It works fine. And should keep these relationships in mind. We'll make use of them. We'll be doing some stuff in phase space, which is just takes you this stuff and uses it straight away. It's not difficult to make the jump from what we're talking about here, which is some kind of real space, but it's trebuchet space, so it's not really, it is quite abstract. But nevertheless, these are useful relations. Go ahead and we mentioned that the contravariant works just as well. Okay. Compare those two, just for the sake of the argument here. Okay, now, I haven't said much about the trebuchet, but here we go back again to lecture 14. This starts on around page 80. And there we're showing what is a little bit unconventional. And that is that when I go to make a quadratic expression, a quadratic form that gives me energy, kinetic energy, as opposed to just length squared, actually velocity squared when you realize that you're working with differential quantities. Here, I've got this thing, not g theta theta or gamma theta phi. I've got, instead of g, I replace that with gamma. And now we're getting the geometry and pretty much the same coefficients here for the projectile, but we've got this extra term here with a different mass, you see. And that we've already derived. That's part of our development that led up to this particular page in lecture 14, the last lecture before this one. So the real reason for doing that, and that's the main thing that we have to do today, is get a relationship between momentum, that involves mass, and it is a covariant quantity. We'll see really why that is, but I think we mentioned it already. But when you do Hamiltonian, it has to be a product, it has to be a function of momentum, and that means you've got to use a contravariant metric to the contravariant gamma, okay, to multiply the covariant momentum. And you get the relationship here between the velocity and the momentum pretty much straight away. And they have the same symmetry as the geometrical metrics. This is the dynamical outgrowth. And this is not conventional, at least not as far as I can see in any of the texts that describe mechanics. But it should be. I mean, it's a nice way to codify this relationship is just as good as some of the relations that you just use all the time with the G factors. Okay, let's see if there's anything else you need to say about that. These are the actual momentum written out, and those are the things we've got to work on here to get the equations of motion just involving coordinates. That's what's called the Riemann equation that I mentioned before. So we got now the algebra starts to fly. We start off with what we know is the total time derivative of the momentum, and we're making use. There's a total time derivative of the momentum. That's P mu, covariant mu, dot minus, and then here's the contravariant in the denominator, so it has the right sense. It is a covariant equation involving the covariant force. So that's what we're going to fill that out. But it's going to require us taking the time derivative, the total time derivative. Now, when you express a time derivative of this thing, we're not going to have a mass that's changing, so that's a constant. We're not going to let the radius of the big beam holding the big mass, not letting that change. That's thankfully 0. But it might be a spring later on. That's another degree of freedom and a coordinate. You'd have to go back and make the Lagrange equation for it. We're not going to change projectile mass, and we're not going to change the projectile radius. Well, this is the radius out on the main arm, and this is the radius of the actual string that's holding the thing that's being thrown. So the only thing that we have to include when we do our total time derivative in a chain sum are the ones that actually change, and that's these two guys, their velocities and their positions. So that's, as I say, you remember when we did Lagrange equations just for polar coordinates, we weren't done just writing equations down. We still have to take the time derivative. We have to do that work. So here it goes. All right, we got some stuff to do here. Okay. And that's kind of the result as far as we would normally go. Okay, to go through there and do lots of derivatives of products, which gives me terms for every product that it's there. And so I get a cross thing. Now what we're deriving here, you see, is a generalization of the Coriolis and centrifugal accelerations, but also just plain old angular acceleration right there. So this is giving me something about the change of this crazy momentum. This is P sub theta. What the heck is that for this giant machine that has this big arm? It's got a momentum, okay? Well, that's what we're trying to figure out. What's its time rate of change? Total time rate of change. And then here's the phi, the thing that's going to fling this projectile. Okay, same deal. I got to do the time derivative, write all those terms out. Okay, so here's where you do your work. This is, you're paid to be a classical mechanic. This is where you collect your paycheck, right? Doing this kind of stuff. Well, and then plugging it into a computer, right? But you know, that comes later. Okay. So the covariant forces, of course, are the driving. That's going to be gravity. I want to point out later on that the Chinese were way ahead of us. They had a trebuchet too, 3000 BCE. Okay, that's a long time before 1500 or 1100 or whatever, the ones that we were talking about before. Okay, but they didn't have a big weight on it. They had lots of Chinese warriors, all each holding a rope and going all at once, and that threw it very nicely if they, you know, wasn't too big a projectile. Forget throwing 5 tons, but they could throw some pretty good rocks. And that's a long time, as far as we know. That was the first trebuchet motion. Anyway, here's what we're dealing with, the forces down here. These are the covariant forces that we have got. This is just the Lagrange force equation, the most elementary equation. Doesn't show symmetry as easily as the other one, but fine. This is one that works no matter what the forces are, whether they have a potential or not, whether they're integrable or not. Doesn't matter. Just, we've got derivatives of them. That's all we want. Okay, so that's something we got to plug into this stuff here when we write this thing, and right now. We're just using the definitions of the momentum, and then, of course, the definitions of the total time derivative of that. But we've got to fill that in with those particular quantities. So this is just what we had before, and now we're going to stick the actual force, the momentum here is equal to this force plus the expression that we got from the, let's see if that's right, from this. Okay. So, let's get that all up here. That's the thing that we have to work on. And basically this is the rest of Lagrange's second equations. This is the one that involves p theta phi. These are the second equation, and then this is the rest of it. So that's where you have to be careful with signs and all that kind of stuff. And go ahead and apply the covariant forces directly there to get this. So here is these gravity forces came from page 69, lecture 14, or before on that particular slides on page 65. So this is where we stand right now. We need to sort all this out to get what would be a computer entry to solve for to make a simulation of a trebuchet. Okay. Now let's see what I've got. I've got this just using this particular version of the force equation. I pick up this term from that, and same thing for this one. I've got lines here showing what we're going to do is we're going to stick f phi into this one, f theta into that one right there, and we'll be pretty close to done after completing that. That's an interesting thing. Now what's cool about this is, and this you'll see happen every time you do this, is that you'll get that the across term, the Coriolis term that shows up here, cancels with one that you already have right here. So that makes things a little simpler. So let me get that to happen on this screen as well as this one, and then I'll go ahead and clean this up a little bit here. Just get them out of there. Okay, so these are the equations that we have now for the f theta in terms of p theta dot, and f phi in terms of p phi dot. And the f's are right here. This one for the big beam, that's what's driving the big beam. And then this is what's the thrower, the rope with a little mass m on it, is taken care of by that particular equation. So go ahead and stick those in there, and that pretty much is what we need to massage a little bit and analyze. Those are the trebuchet equations. That's pretty simple when you write it this way. Now, what we're after is something called the Riemann equation, as I mentioned before. And this is an equation that isolates the accelerations, the angular theta dot dot and phi dot dot. That right now they've got some constants in front of them. This one a different constant, and we need to isolate them. And also, this thing has a whole bunch of variables sitting in front of it. Ditto for this one. So something has to be done to improve that. Now, writing this as a matrix equation, put these two together as a two-dimensional matrix here, gives me a familiar matrix. This is why I say it's worthwhile tracking the gamma metric, the dynamic metric matrix. Okay, it's exactly what we got right here. And we know what the inverse of that is too, so we're just a step away from getting this isolated, getting accelerations isolated. So the Riemann equation of the second kind, the so-called contravariant Riemann equation, so it's sort of in the middle of the main collection of formulas that are down here. See if I can get this to show up. Probably can do it better with ultraviolet. Yes, there we go. So, well, it dies in the paper. I'm after this equation right here. This one is a covariant Riemann equation that's got g mu nu. That's the whole metric sitting in front of the acceleration. That's q dot dot right there, and we isolate it right there. Then these things are called Christoffel coefficients. We will spend time talking about in the next after the break. I decided it would be a good idea to wait till after the break for that. They're called Christoffel symbols by people that have to work with them. Okay, so, but right now we've got the actual gamma matrix sitting there in a nice fashion. So it's just a matter of flipping this thing to get rid of this. Here's the equation as it sits in matrix form with the gravity force right here, and then the Coriolis, actually centrifugal force right there. Funny kind of centrifugal force, so a little bit more needs to be said about that. But the inverse of that is what we need, wouldn't you know it, in order to finish the job here. And this thing I call a super inertia. I mean, it's rotational inertia we're talking about. There's an ml squared, there's an mr squared, there's an m little r squared, a little angle factor. Okay, so we're talking about rotational inertias here, and they're sitting at the bottom of this thing, which is what you would like to have, because you're talking about acceleration, angular acceleration. So this thing right here is going to be multiplying our force input. That's the Riemann equation form right there. All you do is take the inverse of this matrix to clear this out of there and isolate the acceleration. So that's where we are. Now I point out here in the text that the first trebuchet was gravity free, and that's what we're going to study. We're going to study a case where gravity is not a driver. We've got some soldiers that are going, lots of them, that are going to help pull on this trebuchet in 3000 BCE. And look at the dynamics of that later on. But right now I'm just getting the equations in line. Okay? So let's get that all up on the board here. We're really, as I said, we invert the matrix and then use that inverse matrix to get this particular form. Get that on this board as well. Okay. Now, we don't have a whole heck of a lot of time for this is the really dirty part of this lecture, and that is what I call second guessing Riemann equation. In other words, look at that thing and see if you can see how I would have just written this thing down without any Lagrange, without any Hamilton, without anything. I'm just really smart. And I should be able to write the final equation down. Well, you judge that when you read this in the text. This is explained, attempt to explain a way to second guess this very complicated equation here. Now we see centrifugal force here. We imagine that we had a force that was going out from the on a radial line that we imagine going through the projectile, pointing back at the actual center of rotation for the whole big beam. Okay, and we would say, yeah, I could imagine a central force there, r squared plus l squared hypotenuse, there, omega squared hypotenuse. Okay, it's the r l hypotenuse, okay, and that's the kind of force that that would maybe be experiencing. But is that really what's going on here? And the idea is this mass that's on leg L here, that's the thing that has this moment arm, okay. The actual moment arm is this, okay, so you do a little geometry to get that, and hope that maybe you could get what this would B, and that's not too far. I mean, this is what we're looking at right here, and we kind of get it, but it's not quite what we have. This one looks pretty good. I do get that. Okay, so okay, that's one way to finesse this thing without going through any of this. But we still have this. This is a pain in the butt, and that is discussed. We'll move all this stuff to the top of the page. Bingo. Okay, so here's where that discussion begins. I'll get it on all three screens here. Then we're done for the day here. This is a tough one. Okay, so let's go ahead and get that up at the top of the screen here. So we're really trying to get the equations that we're showing there. Maybe what I'll do is I'll leave the equation that we're trying to get there. There it is. Okay, that's theta dot dot equals, and we want to finesse these two terms. We sort of got this one, although I'm sort of suspicious of that thing, because after all, there's a whole joint in between the center of the trebuchet and that particular mass. So, okay, maybe we did finesse it. Now, we really want to second guess that sign right, all that kind of stuff. Whoa, this isn't easy at all. I say it seems paradoxical that the theta coordinate for the main arm feels any torque or acceleration at all. I mean, there's no. It was pointing right at the axis. Where the heck did you get a torque for that? Okay, well we kind of faked it a little bit there, but the device isn't rigid. The centrifugal force has no moment, but its line of action, you see, is going right through there. This guy is a frictionless pivot, okay, can only transform a component along the string. That's the important thing here, is this thing cannot have any torque on that just due to what's going on there. So we have to be careful and see if we can say this thing is causing a negative torque on the big arm, and that's what we're after. We're after how's the acceleration of the big arm being affected by that. And so we write this equation right here. And that does check with the Riemann equation, okay? So let me put that on the right-hand screen here, because that's kind of a victory right there, is that we do have this. So this is kind of like the skater analogy. Something's going on here. This is the skater turning, and the arm flies out, okay? And that's, of course, can be done in reverse if the skater has the ability to pull arms in, and then it goes real fast, then comes to a stop by throwing both arms and legs out sometimes to reduce the rotation. So we're really looking at the time derivative of the total momentum here, and run back through this, and you can finesse these equations without Lagrange, okay? But rot's a ruck. It's not an easy thing to do. And as we get more complicated, of course, it becomes really hard to do mechanics on the fly, like Feynman and those guys used to do. Okay, that's it for today. Have a good break. You deserve it. So do I. We'll see you coming Wednesday next week. Tuesday and Monday apparently are, if I'm not mistaken.
I'm just now hearing it,
Yeah.
so.
Okay.
Yeah, Monday and Tuesday.
All right.